From Cape Canaveral Air Force Station, Florida, United Launch Alliance presents live Atlas V launch coverage. At Space Launch Complex 41, an Atlas V rocket is fueled and ready to launch AFSPC-5 for the United States Air Force.
Range, go for launch. Roger, go for launch.
T-minus 3, 2, 1.
Atlas engine ignition.
Liftoff of the United Launch Alliance Delta IV Heavy rocket.
This is Atlas Mission Control at T-minus 4 minutes and holding. Launch countdown operations are continuing, and the team is not working any issues at this time. We have two 10-minute windows available today. The first opens at 11:05 a.m. Eastern Daylight Time, the second at 12:42 p.m. Good morning, and welcome to Mission Control here at the Atlas Spaceflight Operations Center. My name is Steve Agate. Thank you for joining us. We'll conclude mission coverage about 5 minutes after liftoff. However, before we sign off, I'll be joined by Bill Nye, the science guy, to discuss his role in the LightSail project, which is one of 10 CubeSats aboard this morning's flight. About 10 minutes ago, at T-minus 4 minutes, the launch count entered a planned 30-minute built-in hold. This hold allows launch conductor Scott Barney and his team time to conduct final systems checks and resolve outstanding issues prior to entering the terminal count. As of this point, we remain on schedule for an 11:05 a.m. liftoff. As I just mentioned, Atlas V is launching the Air Force's AFSPC-5 mission. This morning's flight includes the fourth mission of the Orbital Test Vehicle, or OTV-4, as well as 10 CubeSats managed by the National Reconnaissance Office and NASA. Developed by the Air Force Rapid Capabilities Office, the fourth mission of the X-37B OTV will test the performance of an experimental propulsion system. The system was jointly developed by the Air Force Research Laboratory and the Space and Missile Systems Center, as well as a series of advanced material plates developed by NASA. In a manner similar to the Space Shuttle, the X-37B will fly the experiments in space and return them to Earth for an additional analysis following a successful landing. We recently received a final weather briefing from the 45th Space Wing's weather officer. The weather is within the launch commit criteria for today's liftoff. The probability of violating launch constraints is 10%. The ground winds are 5 to 8 knots out of the west-southwest, and the temperature is 81 degrees Fahrenheit. So, we are proceeding towards liftoff with a planned T0 at 11:05 a.m. Eastern Time. ULA is using the Atlas V 501 configuration to launch the AFSPC-5 mission. This is the 54th Atlas V Evolved Expendable Launch Vehicle flight since the inaugural launch in August 2002, and the fifth flight of the 501 configuration. The Atlas V launch vehicle is produced in Decatur, Alabama, and Harlingen, Texas. It comprises a Common Core booster powered by the NPO Ergonomash RD-180 main engine and a Centaur upper stage powered by the Aerojet Rocketdyne RL-10C engine. The AFSPC-5 mission is protected during ascent by the RUAG-built 5-meter diameter payload fairing. On May 7th, the encapsulated payload fairing containing the AFSPC-5 mission was transported to the Vertical Integration Facility, or VIF, and mated to the Atlas V. The VIF is located approximately 1/3 of a mile south of the launch pad. In preparation for launch, the fully integrated Atlas V on its mobile launch platform was rolled from the VIF to the pad at Space Launch Complex 41. This move took place yesterday at approximately 9 a.m. Eastern Time. Trackmobiles are used to transport the Atlas V and its mobile launch platform to the launch pad, a trip that takes about 30 minutes to complete. Once the mobile launch platform reaches its parked position at the pad, the team conducts final securing. Once the pad has been cleared, about 4 hours before launch, the Atlas V is fueled and configured for launch. The Atlas V rocket stands 206 feet tall, or about 21 stories, and weighs more than 757,000 pounds fully fueled. To lift the Atlas V away from the pad, approximately 860,000 pounds of thrust is produced by the RD-180 engine. This is Atlas Mission Control at T-minus 4 minutes and holding. The X-37B orbital test vehicle is designed for vertical launch to low Earth orbit altitudes, where it can perform long-duration space technology experimentation and testing. Upon command from the ground, the OTV autonomously re-enters the atmosphere, descends, and lands horizontally on a runway. Let's take a look at a video detailing today's liftoff.
The following profile details the important events of this mission using approximate times.
5, 4, 3. We have ignition. 2, 1. And liftoff. Liftoff of the United Launch Alliance Atlas V rocket.
The Atlas RD-180 main engine ignites to lift the vehicle away from the pad. Shortly after liftoff, Atlas begins its initial pitch, yaw, and roll maneuvers to attain the proper ascent profile and minimize aerodynamic loads. The Atlas V reaches Mach 1, the speed of sound, at 83 seconds. At 89 seconds, the vehicle experiences maximum dynamic pressure. At 3 minutes 38 seconds, the payload fairing is jettisoned. Approaching booster engine cutoff, the Atlas V is burning propellant at a rate of 1,900 pounds per second, traveling at approximately 8,600 miles per hour, and located 96 miles in altitude and 110 miles downrange. Booster engine cutoff occurs 4 minutes 24 seconds after liftoff. 6 seconds later, the booster stage is jettisoned. The first Centaur main engine start takes place 10 seconds after booster separation.
RC, verify solar radiation acceptable for launch.
Verified.
Launch on time verified.
This is Atlas Mission Control at T-minus 4 minutes and holding. In a few moments, launch conductor Scott Barney will poll the team for the final go to pick up the countdown. 27 engineers and managers will be polled for system status and the readiness to proceed with the launch. This is the final status check before launch for all Atlas vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The readiness poll includes hydraulics, pad water deluge system, electrical systems, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as launch conductor Scott Barney performs the final polling of the team.
Status check to proceed with terminal count. Atlas systems, propulsion, go. Hydraulics, go. Pneumatics,
Go.
LO2. LO2 net 1. Go. Water, go. Centaur systems, propulsion, go. Pneumatics, go. LO2,
Go.
LH2,
Go.
ASGAS,
Go.
electrical systems, airborne,
Go.
ground,
Go.
facility,
Go.
RFFTS,
Go.
flight control,
Go.
instrumentation,
Go.
comm,
Go.
timer,
Go.
GCQ,
Go.
umbilicals, go. ECS,
Go.
redline monitor, go. Quality,
Go.
Ops safety manager,
Go.
ULA safety officer,
Go.
vehicle system engineer,
Go.
anomaly chief,
AC is go.
range coordinator,
Clear proceed.
launch director,
The launch vehicle is ready to launch.
mission director,
You have permission to launch.
proceeding with the count. Timer T0 is planned for 15:05 Zulu. Set count to start 15:01 Zulu.
Roger. T0 is set for 15:05.
Polling is complete and the launch team has been given the go for launch. The countdown will resume approximately 2 minutes from now. From T-minus 4 minutes until launch, you'll be listening to launch conductor Scott Barney and his team performing the final steps in the countdown procedure. You'll hear the team call out that the Atlas LO2 topping has been secured, followed about a minute later by the call-out for transferring the Atlas and Centaur stages from ground facility power to internal battery power. At T-minus 1 minute 55 seconds, the team will command the launch sequencer to start, followed shortly by securing the Centaur LH2 and LO2 topping activity. At T-minus 1 minute 40 seconds, the team will command the flight control system to launch enable and arm the flight termination system. In the final minute, the Atlas tanks will be verified at flight pressures, followed with verification of the Centaur tank pressures. A final status check of the Atlas, Centaur, and AFSPC-5 readiness is conducted at T-minus 25 seconds. Seconds before liftoff, the RD-180 engine ignites and performs a health check prior to lifting the vehicle off the pad. After liftoff, you'll hear the voice of Rob Gannon providing launch vehicle ascent data.
One. Mark. T-minus 4 minutes and counting.
355.
Ground powers enable.
The countdown clock has resumed, and we're proceeding towards an 11:05 a.m. Eastern liftoff, now at T-minus 3 minutes 4 seconds and counting.
Securing LO2 topping.
Atlas tanks to flight pressure.
$250.
FTS internal.
This is Atlas Mission
230.
Control at T-minus 2 minutes 28 seconds and counting. Once the rocket lifts off, it'll reach Mach 1, the speed of sound, in about 83 seconds after launch.
$159.
Vehicle internal.
Launch sequencer start.
$150.
Securing Centaur LH2.
Securing Centaur LO2.
$140.
FCS launch enable.
This is Atlas Mission Control at T-minus 1 minute 31 seconds and counting. The launch vehicle, payload, ground systems, and Eastern Range are go for launch. This is Atlas Mission Control, now at T-minus 1 minute and counting.
Report range status.
This is The Rock. Range is green.
$40.
Stable at step 3.
This is Atlas Mission Control at T-minus 30 seconds and counting.
ECS reduced for launch.
Roger.
25.
Status check.
Go Atlas.
Go Centaur.
Go AFSPC-5.
20. 15.
This is Atlas Mission Control at T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. We have RD-180 ignition and liftoff. Liftoff of the United Launch Alliance AFSPC-5 payload with the Atlas V launch vehicle for the United States Air Force.
Vehicle disturbances are as expected.
You're now hearing the voice of Rob Gannon providing launch vehicle ascent data. Let's listen in for mission progress.
Everything is looking good. Passing 30 seconds into flight, everything looks good. Flight control is nice and smooth. Coming up on 50 seconds into the mission, everything looks good. Flight control is right down the middle, seeing normal disturbances for atmospheric flight. Everything is looking good. Operating parameters look good, vehicle disturbances look good. Open loop steering has been active for a while. Looking just fine. Coming up on Mach 1. And OTV is now supersonic. Passing through max Q. Vehicle disturbances continue to be as expected. We have throttled down to 95% of rated thrust right on time. Body rates are smoothing out. Engine operating parameters continue to look good. Continue to operate at 95% rated thrust. 20 seconds to enabling steering. Vehicle's flying normally. Engine's operating good. And we're proceeding right down the center of the range track, right as expected. Coming up on steering enabled. And we've enabled steering. Vehicle's maneuvering. We are now 25 miles in altitude, 15 miles downrange, traveling at 3,000 miles per hour. Parameters continue to look good. We're now throttling the engine to maintain a constant 2.5 Gs for payload fairing jettison, and we fired the pyro valve, activating the reaction control system on the second stage. Everything's looking good. Continuing to maintain 2.5 Gs in preparation for fairing jettison. Engine continues to throttle as expected to maintain 2.5 Gs. Parameters looking good. Coming up on payload fairing jettison. Everything looking good. Getting ready for fairing. We're at fairing set. And CFR deck has jettisoned as well. Engine is throttling back up to 80% rated thrust, right as expected. Vehicle's operating normally. We've started boost phase chill down. We're now entering our constant 4.6 G acceleration phase in preparation for shutdown. Everything looking good. Coming up on shutdown. Boost phase chill has terminated as expected. We have cutoff. Booster engine cutoff coming up on staging. And we have stage separation. Everything looking good. We have pre-start on LOX and fuel. Ignition, full thrust. RL10 is up and running normally. Good start signature. Operating parameters for the RL10 look good. Vehicle continues to fly right down the center of the range track.
This is Atlas Mission Control at T+5 minutes and 1 second into the flight. We've just heard Rob Gannon report the successful execution of events comprising the early portion of today's mission, and all systems continue to operate nominally. With the mission underway, let's take a look at video highlighting the capability of the X-37B orbital test vehicle. We have ignition.
This is the X-37B. The Boeing-built X-37B Orbital Test Vehicle, or OTV, continues to make history as the first unmanned vehicle to return from space and land on its own. The X-37B provides a highly flexible demonstration testbed platform for a variety of orbital experimental missions.
The X-37B testbed platform is unique because we can tailor our missions to specific user needs and return experiments back for post-flight inspection.
Building on multiple missions, the OTV has proven a reliable fault-tolerant architecture through launch, flight, recovery, and refurbishment cycles. OTV Mission 1 validated the concept with 224 days on orbit. Mission 2 pushed the envelope to 469 days. And Mission 3 not only shattered the record with 674 days on orbit, but also demonstrated the ability to reuse an X-37B flight vehicle.
These missions have proven the reliability and flexibility of the system to support a variety of experiments.
The X-37B offers a consistent and repeatable test platform in the space and hypersonic entry environments. As a reusable system, hosted experiments can be inspected, modified, and flown again at dramatically reduced cost.
Leveraging the existing X-37B infrastructure and reusing the platform allows users to focus their investment on the experiment and developing new technologies.
Responsive to rapid integration, the X-37B can fly and test multiple new technologies, reduce technical risk early in product design, and validate system performance. Integrated experiments leverage onboard power, telemetry, orbital maneuvering, thermal and attitude control to enhance test parameters.
The partnership between Boeing, Space Florida, NASA, and the Air Force is establishing a capability for the X-37B to launch, land, and process for reflight at Cape Canaveral. This will further reduce cycle time, providing even more responsive access to space.
Ready to fly tomorrow's next-generation space-based technologies, today's X-37B enables affordable access to orbit.
The reliability, reusability, and responsiveness of the X-37B will fundamentally change how we perform future space missions.
As I mentioned earlier, in addition to OTV-4, today's flight includes 10 CubeSats. One of those CubeSats is LightSail, developed by the Planetary Society. And I'm pleased to welcome Planetary Society CEO and science guy, Bill Nye.
Thank you, Steve. It's great to be here.
Well, Bill, thanks so much for joining me. It's a thrill and an honor to meet you.
We're in the control center, for crying out loud. How cool is this?
Doesn't get much better.
Do we call this mission control?
Absolutely.
It's cool.
Okay. The Planetary Society has a CubeSat named LightSail on today's mission. Now, would you give us a quick overview of the project?
Yeah, so this may surprise you, us, anybody, but light has momentum, even though it has no mass. So if you can get, I mean, it's even when we're sitting here and light's hitting us, impinging upon us, we are getting a tiny, tiny, tiny push from the photons. Well, if you're out in space where there's nothing to stop you, and you have a big enough object, big enough sail in this case, and a low enough mass spacecraft, it gets pushed. And so Carl Sagan, my old professor, talked about this in 1976. They wanted to have a mission to catch up with Comet Halley, Halley's Comet. And that mission was canceled in exchange for the space shuttle. I guess there were some other technical problems. But the guys involved were Carl Sagan, Lou Friedman, my predecessor at the Planetary Society, and Bruce Murray, who was the head of the Jet Propulsion Lab at that time. And they wanted to have a solar sail to prove that the technology would work. It's one thing to sit in physics class and show that this should be possible, but it's another to really do it. As Tex Johnston, the test pilot on the Boeing 707, said, "One test is worth 1,000 expert opinions." Mm-hmm. So those three guys started the Planetary Society in 1980. I joined. I've been a member ever since. And then I joined the board in 1997, and everybody has been talking about a solar sail since then. I mean, since 1976, people have talked about solar sails. And so the Planetary Society got some funders, especially Andrian from the Carl Sagan's estate, Andrian's Carl Sagan's widow, from his estate, and we tried to fly in 2005, Cosmos 1, but it ended up in the drink. It's in the Barents Sea, somewhere in the Arctic Ocean. And so 10 more years have gone by, and we've rekindled the idea and embraced the standard called CubeSat, which is just 10 centimeters by 10 centimeters by 10. But ours is a 3-unit CubeSat, so it's 10 by 10 by 30 centimeters, smaller than a shoebox, everybody. And then the sail that will come out of it is this super shiny mylar. And another just sort of surprising thing until you think about it, if it's shiny, specular, like a mirror, the photon bounces off going this way and goes back that way, so you get twice as much momentum as if it were black, fully absorbent, black body, what have you. So it's just like, you're kidding. Like, that's going to work. So this, out of this little box, these really cool, really wonderful material. It's high cobalt steel, which was manufactured at the Air Force Research Lab at Kirtland Air Force Base in Albuquerque, New Mexico. These things come out 4.7 meters, and the sail then is 32 square meters. I mean, it's an enormous thing with this little, less than 10 kilo CubeSat. And so we're very hopeful that the thing will deploy properly, sunlight will hit it, and get a push. Now, this mission, and I love you all, of course, at Atlas V land, but it's not going especially high. So we're going to get dragged down by the atmosphere pretty quickly. But this is a test flight. There's two things that we really want to verify. Telemetry with the ground, which includes pictures from our cameras. We have really elegant cameras built by Aerospace Corporation. And we want to see the sails deploy, because if you're scoring along with us, NASA launched a spacecraft called NanoSail D. And for those of you who are normal or whatever, D, capital D in aerodynamics means drag. So this thing was designed to be dragged down. And the sails didn't deploy for about 6 weeks. And no one's really sure why that was. It's just stuck, mechanically stuck probably. And then every time you go around the Earth, you get hot and cold, and it shook loose. But we are pretty confident we have solved that deployment problem. There is no thermal vacuum chamber on Earth big enough to have all 4 sails deploy at once from our little spacecraft. So we're going to fly it in space and see if it really works, and we're pretty confident. And just remind everybody, this was built by our members, 40,000 plus people around the world who just thought this was an intriguing and wonderful thing to experiment with. And it's a technology that we strongly believe will enable all kinds of missions to the moon, to asteroids, to Mars, and the other just really sort of practical application of a solar sail is to get in an orbit closer to the sun than the Earth. And then instead of getting pulled in, because when you're closer to the sun, you'd have to go faster, let the solar sail keep your position, so-called station keeping with the Earth. And that could have all kinds of advantages for monitoring solar weather and for looking for Earth orbit crossing asteroids. What you really want to do is look for those in the infrared spectrum, because in the visible, it's, as we say, it's like looking for charcoal in the dark. It's really hard to see. But with the solar sail, we strongly believe that all sorts of universities, institutions, and especially the Air Force is quite interested in this technology, and we have worked real hard to keep the cost very low, and the compactness of it, keep the space very small. The space, that's a pun. The volume it takes up very small. So it's very exciting to be on the Atlas V.
Okay, well, ULA has launched 5 CubeSat missions already. I'd like to know how important are these missions in terms of the experience they provide to the students, the research groups, as well as the science and technology advancements we gain from these really low-cost investments.
Yeah, so the CubeSat is very small for starters, but the other thing is it's standardized. So you can go online and buy solar panels that are robust enough to take the hard vacuum of space in the sun, on the sun side and the night side over and over. Without the thermal problems you would have with a homeowner's solar panel. And you can get electronics, you can get software, you can get software modules, and these things are becoming standardized, which has enabled universities. But the U.S. Air Force is quite interested in them, and Jet Propulsion Lab and Applied Physics Lab have both expressed strong interest. We have a lot of members there. Strong interest in the success of this particular style of CubeSat because it has its own propulsion. When you're using solar energy, it's there all the time. Mm-hmm. And so although it's a very small thrust, it's continuous rather. And so you can go hypothetically as far as you want in space.
Well, given the Planetary Society's unique mission, I imagine the CubeSats are an important part of its puzzle.
Oh, yeah. So one of the problems we had with this Cosmos 1 Russian-built solar sail in 2005 was every part of it was custom-made, every part of it. But now it's launching from a standard P-pod, which is another tortured acronym. I think it has the word PICO satellites in there. Yeah. And so it's a jack-in-the-box that is a standard size, a standard thrust spring with a standard release mechanism, a burn wire, that's all figured out. So that part of the mission that's been solved. And you guys at ULA have solved it, would you say 5 times?
5 times.
Yeah, so it's very high reliability. And I'll tell you, our members, we launched on a Russian rocket, 2005, and it ended up in the ocean. They would not, they're very happy to be aboard a U.S.-built, high-reliability, big-time rocket. So thank you, guys.
Well, thanks a lot. Well, I'd like to shift gears just a little bit, and I think you'll find this interesting. It seems we have something in common. Each time I host...
Even more?
Even more. And each time I launch I'm in an Atlas countdown and host this broadcast, we get questions from our viewers about my tie.
Your tie. Oh, yes. It has pictures of a rocket.
That's right.
It has a space shuttle.
That's right. And I know that you're known for your ties as well.
Yes. But you choose not to wear bow ties.
That's right.
Takes all kinds, Steve. I don't get it.
And there's a reason for it. This tie has a history. And the history of this tie is, in 1998, when I was working on the other side, I was one of the folks that...
when you say the other side,
the other side
of the glass.
No, the other side of the river here, the Banana River, which is separates us from the Merritt Island, which separates from the Indian River to the mainland. The NASA missions are launched on the other side. We're actually on Cape Canaveral.
Yeah, so we're on an Air Force base.
We're on an Air Force
working in the civilian zone.
That's correct. Yeah. And I got to work on the STS-95 mission. I got this tie when I was actually called upon to set some of the switches up on Discovery for John Glenn's flight.
So you threw some switches.
That's
and
correct.
It didn't go wrong.
Everything went well. And so with this Atlas rocket, when I was asked to do this countdown, I decided, hey, I'll wear this Atlas tie. But most importantly, for all the plus count missions that I do on Delta and for the Atlas ones, I always wear my Snoopy tie pin.
And Snoopy is for safety.
That's right. Since
now, let me ask you,
1967.
I don't need to know. I haven't seen every broadcast. But when you wear the tie, do you also wear a shirt?
Yes, I always wear a shirt.
I'm sure you could pull it off, but I think it would distract some of the viewers.
A white shirt for the Atlas missions and a blue shirt for the Delta missions.
I'll take
there's a reason for that. And there's a reason for that,
Why
too.
is that?
Well, the white shirt is our ULA launch shirt for Atlas for me.
Oh, it's got ULA inside.
Absolutely.
Yeah, well, there you go.
One more thing for our viewers to see.
Yes.
And
we don't need to see much more, Steve.
Well,
That's
there's
good.
a blue shirt for the Delta missions, and that's a different tie that was picked out by my wife Maria and daughter Carolyn. Oh, it's blue for Delta Blue and green for Go.
It's a lot. So this one has stars. And it's actually made from the Sophia straight tie. Sophia was a Stratospheric Observatory for Infrared Astronomy. It's a 747 special performance with the double hinge rudder. And they open the door in the stratosphere and take pictures of planets, celestial objects. So it's a space tie.
Well, Bill, I want to thank you for being here.
Oh, no, it is I who must thank you. And seriously,
seriously,
our members of the Planetary Society are very excited to be on an Atlas V. I'm not joking you. You know, we had, in 2005, as part of the legacy of Carl Sagan, and Drian, his widow, and Discovery and these other entities funded the Cosmos 1 solar sail, which was built largely in Russia and flew on a Russian Cold War repurposed submarine rocket, like for real. And it ended up in the Barents Sea, which is somewhere in the Arctic Ocean. It's a region of the Arctic Ocean. And our members expressed a lot of concern about that. And so everybody's very happy to be on this very reliable, time-tested, very reasonably priced launch vehicle. So thank you for letting us get a ride.
Well, best of luck with LightSail. It's a fascinating project, and we're looking forward to following its progress.
Oh, yes. So it will deploy, if we don't do anything, it'll deploy automatically in 28 days. And you have to wait, everybody. I'm sorry. We launched these CubeSats. Everybody waits so that they'll separate in space, so they won't be too close together. It's just actually the cheapest way to do it. Just let them drift apart. So we hope we'll deploy sooner than that, but within the month, we're going to run the big test.
Always giving more bang for the buck, right?
That's our hope.
Okay, that's
Thanks very
great.
much.
Well, thank you, Bill. And I invite our viewers to share their photos and launch stories about the launch trays and their traditions on the hashtag #GoForLaunch.
Go for launch.
Okay. We'll now conclude our coverage, and I'd like to thank Rob Gannon for his support of today's show. And for more information about the Atlas V, please visit our website, ulalaunch.com, or join the conversation on Twitter and Facebook. We'll complete our live coverage with another look at today's Atlas V launch. I'm Steve Agate, and on behalf of the entire ULA launch team, thanks for joining us, and have a great day. 5, 4, 3, 2, 1, 0. We have RD-180 ignition and liftoff. Liftoff of the United Launch Alliance AFSPC-5 payload with the Atlas V launch vehicle for the United States Air Force.
Vehicle disturbances are as expected.
You're now hearing the voice of Rob Gannon providing launch vehicle ascent data. Let's listen in for mission progress.
Everything is looking good. Passing 30 seconds into flight, everything looks good. Flight control is nice.